The invisible universe. Dark matter and dark energy, the phantom forces that control 95% of reality. Everything you've ever seen, touched, or known, every star in the night sky, every planet, every atom in your body, every ray of light that has ever existed, amounts to less than 5% of the universe. The other 95% is invisible. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. You cannot see it, touch it, or detect it with any conventional instrument. Yet it's there everywhere, right now, passing through your body at this very moment. Billions of particles streaming through you, through the earth, through everything, as if the entire visible universe were nothing more than. This is not philosophy. This is not speculation. This is the unsettling reality confirmed by a century of astronomical observations and, potentially, by breakthrough detections made just weeks ago in November 2025. Scientists call these invisible forces dark matter and dark energy. Dark matter makes up roughly 27% of the universe and holds galaxies together through its gravitational pull. Dark energy comprises about 68% of reality and is tearing the universe apart, accelerating its expansion. Together, they constitute 95% of everything that exists. We live in an invisible universe, and we're only now beginning to understand what that truly means. Chapter 1: The Discovery That Shook Physics. The story begins in 1933, in the depths of the Great Depression, when a brilliant and temperamental Swiss astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster. Located about 320 million light-years from Earth, Zwicky was measuring how fast individual galaxies were moving within the cluster. What he found made no sense. The galaxies were moving so fast, at speeds exceeding 1,000 kilometers per second, that the gravity from all their visible mass shouldn't have been enough to hold the cluster together. By all calculations, these galaxies should have been flung into intergalactic space long ago, scattered like sparks from a cosmic explosion. Yet there they were, bound together in a tight group. Zwicky calculated that the cluster needed about 400 times more mass than could be seen to generate enough gravity to keep those galaxies from flying apart. He proposed that some invisible form of matter, which he called Dunkel Materie, German for dark matter, must pervade the cluster, providing the additional gravitational glue. The astronomical community largely ignored him. Zwicky was known for his abrasive personality and controversial ideas, and dark matter seemed too outlandish, too convenient an explanation. Surely there was a simpler answer. Perhaps the galaxies weren't really moving that fast. Perhaps the measurements were wrong. Perhaps Zwicky himself was wrong. For 4 decades, dark matter remained a fringe concept dismissed by mainstream science. Then came Vera Rubin's. Chapter 2: The Rotation Curves That Changed Everything. In the 1970s, American astronomer Vera Rubin was studying spiral galaxies, majestic pinwheels of stars like our own Milky Way. She was measuring how fast stars orbit around galactic centers at various distances. According to Newton's laws of gravity, which had successfully explained planetary motion for 3 centuries, stars farther from the galactic center should orbit more slowly, just as outer planets in our solar system orbit the sun more slowly than inner planets. The visible matter in galaxies is concentrated toward the center, so gravity should weaken with distance, slowing down the outer stars. But that's not what Rubin found. Using state-of-the-art spectrographs at Kitt Peak National Observatory, she measured the rotational velocities of 21 spiral galaxies with unprecedented precision. What she discovered was shocking. Stars at the edges of galaxies were moving just as fast as stars near the center, sometimes even faster. Unless there was far more matter in these galaxies than could be seen. Unless galaxies were embedded in vast, invisible halos of dark matter extending far beyond their visible edges. These dark matter halos could contain 5 to 10 times more mass than all the visible stars, gas, and dust combined. Rubin's observations, published throughout the 1970s and 1980s, provided overwhelming evidence that Zwicky had been right all along. Dark matter wasn't just present in galaxy clusters. It was everywhere, dominating the mass of every galaxy in the universe. The invisible universe was real. Chapter 3. Building reality from nothing. But dark matter isn't just present in the universe. According to our best cosmological models, dark matter literally created the universe as we know it. Go back to the beginning. In the first moments after the Big Bang, the universe was an almost perfectly smooth soup of energy and matter, with only the tiniest fluctuations in density, quantum ripples that would have been invisible to any observer. Ordinary matter, the atoms that make up stars, planets, and people, was buffeted by intense radiation filling the early universe. Photons of light constantly collided with atoms, preventing them from clumping together under gravity. Ordinary matter was like sand in a windstorm, unable to settle and accumulate. But dark matter was different. Dark matter didn't interact with light or radiation. It felt only gravity. Those tiny quantum fluctuations in dark matter density began to grow, pulling more dark matter toward them through gravitational attraction. Over millions of years, these dark matter clumps grew larger and larger, creating gravitational wells, invisible valleys in the fabric of spacetime. Once the universe cooled enough that radiation no longer dominated, ordinary matter fell into these dark matter wells like water flowing downhill. Gas collected at the centers of dark matter halos, compressed by gravity, heated up and ignited into the first stars. Those stars gathered into the first galaxies. Galaxies clustered along dark matter filaments stretching across hundreds of millions of light years, creating the cosmic web, the largest structure in the universe. Without dark matter, none of this would have happened. The tiny density fluctuations in ordinary matter alone could never have grown quickly enough. By the time ordinary matter could start clumping together, the universe would have expanded so much that nothing larger than dwarf galaxies could form. There would be no Milky Way, no stars like our sun, no rocky planets, no life. Dark matter didn't just shape the universe. Dark matter made the universe possible. Computer simulations called n-body simulations which track the gravitational interactions of billions of particles over cosmic time, confirm this picture with stunning accuracy. When scientists run these simulations with the right amount of dark matter, they produce a universe that looks exactly like the one we observe. Galaxies distributed in a cosmic web of filaments and voids, with the right sizes, shapes, and clustering properties. When they run the same simulations without dark matter, they produce a universe utterly unlike our own. Chapter 4. The Bullet Cluster, Seeing the Invisible. One of the most dramatic pieces of evidence for dark matter comes from a cosmic collision observed in 2006 in a system called the Bullet Cluster, located about 3.8 billion light-years from Earth. The Bullet Cluster formed when two massive galaxy clusters, each containing hundreds of galaxies and vast clouds of hot gas, collided at speeds of several million miles per hour. This was one of the most energetic events in the universe since the Big Bang. During the collision, something extraordinary happened that allowed astronomers to see dark matter for the first time. When the clusters collided, the hot gas from each cluster, ordinary matter observable in X-rays, slammed into each other, producing a shock wave like a cosmic bullet. The gas clouds, being made of ordinary matter, interacted through electromagnetic forces, slowed down, and collected at the collision site in the center of the combined cluster. But the dark matter halos surrounding each cluster didn't interact. They passed right through each other like ghosts, continuing onward with barely any disturbance. By using gravitational lensing, measuring how the combined cluster bends light from galaxies behind it, astronomers could map where the mass actually was. And what they found was stunning. Most of the mass wasn't where the hot gas was. Most of the mass was collected around the galaxies themselves, which had also passed through the collision without much interaction. This was the smoking gun. The Bullet Cluster provided direct observational evidence that dark matter exists as a separate substance from ordinary matter, that it doesn't interact except through gravity, and that it outweighs visible matter by about 5 to 1. The invisible universe had been photographed. Chapter 5, November 2025, First Contact. For nearly a century, dark matter remained stubbornly invisible despite increasingly sophisticated searches. Physicists built detectors deep underground, shielded from cosmic rays, waiting for dark matter particles to collide with ordinary atoms. They found nothing. They searched for dark matter at the Large Hadron Collider, trying to create it in particle collisions. They found nothing. They looked for indirect evidence, signs of dark matter particles annihilating each other in space, releasing detectable radiation. They found maybe something. In November 2025, Professor Tomonori Totani from the University of Tokyo published a bombshell paper analyzing data from NASA's Fermi Gamma Ray Space Telescope. He reported detecting a halo of high-energy gamma rays extending from the center of the Milky Way. Gamma rays with precisely the energy, intensity, and distribution pattern predicted if dark matter particles were colliding and annihilating in the galactic center. The gamma rays had an energy of 20 gigaelectronvolts, 20 billion electron volts, an enormous amount of energy. Their distribution matched the expected shape of the Milky Way's dark matter halo with remarkable precision, and their characteristics fit the theoretical predictions for WIMPs, weakly interacting massive particles, hypothetical dark matter particles with masses about 500 times that of a proton. If this is correct, to the extent of my knowledge, it would mark the first time humanity has seen dark matter, Totani stated. And it turns out that dark matter is a new particle not included in the current standard model of particle physics. The scientific community responded with cautious excitement. If confirmed by independent analyses and observations, this could be one of the most important discoveries in the history of physics, direct observational evidence of the substance that makes up a quarter of the universe. But as of early December 2025, the finding awaits independent verification. Other astrophysical processes could potentially produce similar gamma-ray signals. The hunt continues, but for the first time we may be closing in on dark matter's true identity. Chapter 6: The even stranger mystery, dark energy. If dark matter is strange, dark energy is utterly bizarre. In 1998, two teams of astronomers studying distant supernova explosions made a discovery that would win them the Nobel Prize and upend our understanding of the cosmos. They were trying to measure how fast the universe's expansion was slowing down due to gravity pulling everything back together. Instead, they found the opposite. The universe's expansion was speeding up. This made no sense. Gravity is attractive. It pulls things together, not pushes them apart. The expansion of the universe should be slowing down over time, possibly eventually reversing into a cosmic collapse. That had been the expectation for decades, but the data was unambiguous. Distant supernovae were fainter than expected, meaning they were farther away than they should be if the universe's expansion had been constant or slowing. Something was pushing galaxies apart with ever-increasing force, overcoming gravity and accelerating the expansion. Scientists called this mysterious force dark energy, though it's probably not energy in any conventional sense. We don't know what it is. We don't know where it comes from. We can't detect it except through its gravitational repulsion on cosmic scales. What we do know is terrifying in its implications. Dark energy makes up roughly 68% of everything that exists in the universe, more than twice as much as dark matter, more than 13 times as much as all ordinary matter combined. And it's winning. Dark energy is tearing the universe apart. Chapter 7: The Fate of Everything. Dark energy's dominance means the universe has a fate far stranger and lonelier than anyone imagined. For the first 9 billion years after the Big Bang, matter, both dark and ordinary, dominated the universe. Gravity was winning, pulling structures together, allowing galaxies to form and cluster. But around 5 billion years ago, about the time our solar system was forming, dark energy began to take over. As the universe expands, matter becomes more diluted. Galaxies spread farther apart. But dark energy doesn't dilute. It remains constant throughout space and time. So as the universe grows larger, dark energy's effect grows stronger relative to matter's gravitational pull. The consequences are profound. Galaxies that aren't already bound together by gravity are now accelerating away from each other. The space between galaxy clusters is growing faster and faster. Eventually, distant galaxies will recede from us faster than light can travel, disappearing beyond a cosmic horizon from which no information can ever reach us. In about 100 billion years, every galaxy outside our local group will have vanished from view. Future astronomers in distant galaxies, if any civilizations last that long, will look out and see only their own galaxy surrounded by darkness. They'll have no way to know that a vast universe once existed beyond their shores. They'll have no evidence for the Big Bang, no way to measure cosmic expansion, no way to discover dark energy. They'll live in a universe that appears static, eternal, and bounded. Precisely the universe that scientists in the early 20th century believed we inhabited before Edwin Hubble discovered cosmic expansion in 1929. In the far future, entire eras of cosmic discovery will be impossible. We're living in a privileged age, perhaps one of the only epochs when the universe's history is still readable in the sky. And still farther in the future, trillions of years from now, dark energy will have torn everything apart. First, galaxy clusters will dissolve. Then galaxies themselves will be shredded. Eventually, solar systems will be disrupted, planets flung from their stars. Some physicists have even speculated about a Big Rip scenario where dark energy becomes so strong that it tears apart atoms themselves, ending the universe in a catastrophic disintegration of all matter. But there's uncertainty here. Recent observations from the Dark Energy Spectroscopic Instrument DESI, published in 2025, hint at something even stranger. Dark energy might not be constant after all. The data suggests dark energy could be evolving over time, its strength changing as the universe ages. If true, this changes everything. Maybe dark energy will weaken, allowing matter to reassert control. Maybe it will grow stronger, accelerating the Big Rip. Maybe it will do something completely unexpected that we haven't even imagined yet. The universe's fate hangs in the balance, controlled by a force we don't understand acting according to rules we haven't yet discovered. Chapter 8: What is dark matter? Despite decades of searching, we still don't know what dark matter actually is. But we have clues, and those clues point to several possibilities. The WIMP hypothesis. The leading candidate has long been WIMPs, weakly interacting massive particles. These would be fundamental particles, perhaps left over from the Big Bang, that have mass, making them dark matter, but interact with ordinary matter only through gravity and possibly the weak nuclear force, making them weakly interacting. WIMPs would have masses 10 to 1,000 times that of a proton. They'd be heavy enough to move slowly, making them cold dark matter, allowing structures to form as observed. And there would be vast numbers of them, hundreds per cubic centimeter in the solar neighborhood, billions streaming through your body every second. The November 2025 gamma-ray detection by Totani suggests WIMPs with masses around 500 times a proton's mass, right in the middle of theoretical predictions. If confirmed, this would vindicate decades of theoretical work and experimental searches. Axions. Another possibility is axions, hypothetical particles with extraordinarily tiny masses, perhaps 1 trillion times lighter than an electron. Axions were originally proposed to solve a problem in particle physics unrelated to dark matter, but they could serve double duty. Axions would behave very differently from WIMPs. They'd exist in vast clouds with quantum properties, creating weird wave-like patterns in space. Some theories suggest axions could convert into detectable photons in strong magnetic fields, providing a potential detection method. Primordial black holes. A more exotic possibility. Maybe dark matter isn't made of particles at all. Maybe it's made of black holes. Not stellar mass black holes formed from dying stars, but primordial black holes, objects that formed in the extreme conditions of the early universe, less than a second after the Big Bang. These could range from the mass of asteroids to thousands of times the Sun's mass. Primordial black holes would be completely invisible, interacting only through gravity, exactly like dark matter. Recent calculations suggest they could account for at least some of the missing mass, though probably not all of it. Physicist Stephen Hawking championed this idea before his death, and observations are actively searching for evidence. Interestingly, researchers estimate a primordial black hole could pass through our solar system about once every 10 years, close enough to potentially detect through its gravitational effects on planets' orbits. The dark sector, perhaps the most mind-bending possibility. Dark matter might not be a single type of particle, but an entire parallel universe of particles, a dark sector as rich and complex as the visible matter we know. In this scenario, dark matter could include dark atoms, dark molecules, dark chemistry, maybe even dark stars and dark planets made of dark matter. This dark universe would exist right alongside ours, overlapping in space but interacting only gravitationally. We'd be blind to it as it would be blind to us. Yet its gravity would shape our cosmos, and our gravity would shape its structures. Two universes, interpenetrating but invisible to each other, dancing an ancient gravitational dance. Chapter 9, or maybe it doesn't exist. In November 2025, just weeks after Tautani's potential dark matter detection, another bombshell paper appeared suggesting something radical. Maybe dark matter and dark energy don't exist at all. Professor Rajendra Gupta from the University of Ottawa proposed that what we interpret as dark matter and dark energy are actually illusions caused by the fundamental forces of nature gradually weakening as the universe ages. In Gupta's model, the coupling constants, numbers that determine the strength of forces like gravity and electromagnetism, slowly change over cosmic time and across space. This varying strength produces effects that look exactly like dark matter at small scales, holding galaxies together, and dark energy at large scales, accelerating cosmic expansion. The model's elegance is striking. It explains galaxy rotation curves, galaxy clustering, gravitational lensing, and cosmic expansion using the same mathematical framework, without invoking any invisible substances. It even resolves certain tensions in cosmology, like the Hubble tension, discrepancies in measurements of the universe's expansion rate. This would mean the century-long search for dark matter particles has been chasing a phantom. The billions spent on underground detectors and particle accelerators have been looking for something that doesn't exist. Dark matter and dark energy would join luminiferous ether and phlogiston in the graveyard of discarded scientific concepts. But there's a problem. Gupta's model, while intriguing, struggles to explain certain observations as easily as the standard dark matter model does. The bullet cluster, for instance, is difficult to explain without invoking actual dark matter, and most physicists remain unconvinced that modifying the laws of physics is simpler than accepting that most of the universe is made of something we haven't detected yet. The debate continues. Maybe both camps are partially right. Maybe there is dark matter, but less than we think, with the rest explained by modified physics. Maybe the truth is something neither side has imagined yet. We're living through a scientific revolution in real time, watching as two fundamentally different visions of reality compete for acceptance. One of them will be remembered as one of the greatest breakthroughs in physics. The other will be a fascinating wrong turn, a reminder that even our most confident theories can be overturned by better explanations. History hasn't yet decided which is which. Chapter 10. The dark matter-dark energy connection. Recent research suggests something even stranger. Dark matter and dark energy might not be independent phenomena. They might interact with each other in ways we're only beginning to understand. In December 2025, researchers from the Shanghai Astronomical Observatory published simulations showing that if dark matter can decay into dark energy or vice versa, it dramatically affects how galaxies form and align with cosmic structures. In their IDEI model, where dark matter slowly transforms into dark energy, dark matter halos become more strongly aligned with the cosmic web's filamentary structures. In the IDEI model, where dark energy converts into dark matter, the alignment weakens. These differences would be measurable by upcoming surveys like the China Space Station telescope. If we can detect these alignment patterns, we might finally understand whether dark matter and dark energy are truly separate phenomena or two faces of a single underlying reality. Think about what this means. The two substances that dominate the universe might be transmutable, flowing into and out of each other over cosmic timescales. Dark matter could be the parent substance that decays into dark energy, driving cosmic acceleration. Or dark energy could be the primordial field that occasionally condenses into dark matter particles. This would elegantly explain why dark energy's effects only became dominant recently in cosmic history. Perhaps there simply wasn't enough of it earlier because most of it was still in the form of dark matter. Or perhaps the interaction goes both ways, with dark matter and dark energy in a cosmic balance, their relative proportions shifting as the universe evolves, creating the complex tapestry of structure we observe. We won't know until we measure it, but the possibility alone is breathtaking. The two greatest mysteries in physics might be intimately connected, two aspects of a deeper phenomenon we're only now beginning to glimpse. Chapter 11. Living in the Dark Universe. What does it mean to live in a universe that is 95% invisible? It means every certainty we have about reality is built on a foundation we don't understand. The atoms that make up your body, the earth, the sun, all the stars you can see, they're not representative of the universe. They're a tiny minority, a thin frosting on an invisible cake. It means the universe is fundamentally alien in ways we're still grappling with. We evolved to perceive electromagnetic radiation, light, because that's what interacts with the matter we're made of. Our eyes, our technologies, our intuitions about how reality works are all tuned to that 5% of existence that plays by familiar rules. The other 95% plays by different rules. Dark matter passes through you right now, billions of particles every second, moving at hundreds of kilometers per second, streaming through your body as if you were empty space. You don't feel them, you can't sense them, they don't care that you exist. It means humility. For all our technological sophistication, for all our scientific understanding, we're like blind people describing an elephant. We've felt gravity, we know dark matter and dark energy exist, but we haven't truly seen them, touched them, understood them. It means opportunity. We're living at the dawn of a new age of discovery. The invisible universe is starting to reveal itself. In the past few months alone, we've seen potential direct detection of dark matter particles, evidence that dark energy might be changing over time, and theories that could eliminate the need for both entirely. This is the most exciting time in cosmology since the discovery of cosmic expansion. Every new telescope, every new detector, every new observation has the potential to revolutionize our understanding of reality itself. And it means we're part of something far stranger and grander than our ancestors ever imagined. The universe isn't just big, it's mostly invisible. It isn't just old, it's being torn apart by forces we don't understand. It isn't just mysterious, it might be fundamentally unknowable in ways we're only beginning to appreciate. We're cosmic explorers mapping an invisible landscape, charting territories that can never be seen, only inferred. We're detectives piecing together clues to solve the greatest mystery ever confronted by human intelligence. We live in a dark universe, but we're bringing light to it one discovery at a time. Epilogue: the hunt continues. As of December 2025, the invisible universe remains mostly invisible, but cracks are appearing in the darkness. The Fermi telescope may have seen dark matter annihilating in our galactic center. The Daisy survey suggests dark energy is evolving. The Vera C. Rubin Observatory, beginning operations soon, will map the sky with unprecedented depth, revealing the large-scale structure shaped by dark matter. The China Space Station telescope will measure how dark matter halos align with cosmic filaments. Underground detectors continue their vigil, waiting for that unmistakable signal of a dark matter particle colliding with ordinary atoms. The Large Hadron Collider continues searching for exotic particles that could be dark matter candidates. Radio telescopes scan for the faint signals of axions converting to photons. Theorists refine their models, simulations grow ever more sophisticated, and alternative theories challenge the dark matter paradigm itself. Somewhere in this flood of data and ideas, truth is waiting to be found. Perhaps dark matter is made of WIMPs, and Totani's gamma rays are our first glimpse of them. Perhaps it's axions or primordial black holes or something we haven't thought of yet. Perhaps it doesn't exist at all, and we need to rewrite the laws of physics. Perhaps dark energy is a cosmological constant. Einstein's greatest blunder turned out to be his greatest insight. Perhaps it's a dynamic field evolving over time. Perhaps it's evidence that we don't understand gravity on cosmic scales. Perhaps dark matter and dark energy are connected, two faces of a single phenomenon. Perhaps they're entirely separate. Perhaps the question itself is wrong, and the real explanation is something we can't even imagine yet. But here's what we know for certain. 95% of the universe is invisible to us. We're swimming in dark matter, being pushed apart by dark energy, living in a cosmos dominated by forces we barely comprehend. And we're closer than ever to understanding it. The invisible universe won't stay invisible forever. Already, we're learning to see in new ways through gravitational lensing, through the rotation of galaxies, through the acceleration of cosmic expansion, through the potential signature of particle annihilation in gamma rays. We're teaching ourselves to see the invisible, to measure the intangible, to comprehend the incomprehensible. This is humanity's greatest quest, to understand the nature of the reality we're embedded in, even when 95% of that reality is hidden from view. The hunt for dark matter and dark energy will define physics in the 21st century, the way quantum mechanics and relativity define the 20th. It will take decades, perhaps centuries, to fully understand these phantom forces. But understand them we will, because that's what humans do. We look at the darkness and refuse to accept ignorance. We build instruments to extend our senses into realms we were never meant to perceive. We construct theories to explain the inexplicable. We persist. The invisible universe is vast, but human curiosity is vaster still. And somewhere out there in the dark matter halos surrounding galaxies, in the dark energy permeating the void, in the quantum foam of spacetime itself, the answer is waiting. The darkness is deep, but we're bringing the light.